Let's continue with the so-called Taylor's theorem. It states that if a function f is analytic in a neighborhood, that's the interior of a circle with center at set 0 and radius r0, then the function f of z can be represented as an infinite series in the following way. So the elements of the series are like this: an times z minus z0, the center of this circle, in the power of n. And this is valid for all z inside this circle. Moreover, this coefficients an is given by the following expression. It's the nth derivative of the function f at the point z0 divided with the faculty of n. Recall what the faculty of n is. It's equal to n times n minus 1 times n minus 2 and so on, and the faculty of 1 and 0 are defined to be equal to 1. We are not going to prove this theorem. We are going to say instead that the most common Taylor series are the Maclaurin series, and these Maclaurin series, they are obtained in the case when we let set 0 be equal to 0. Let's now give an example of the use of this theorem. If, for example, we have the function f of z is equal to the exponential function of z, then we know that the derivative of the function f all derivatives are in fact equal to the exponential function. So letting set 0 be equal to 0, that means that we are going to find the Maclaurin series. Then we know that the nth derivative of the function f at the point 0 is equal to the exponential function of 0, which is just equal to 1. So this an, which are given by the nth derivative of set 0, in this case set 0 is 0, over this n faculty is just equal to 1 over n faculty. So in this case we obtain a very simple expression for this infinite series. It looks like this. And since the function f is analytic in the whole complex plane, we do not have any limit for the radius here, so we may put this radius as large as we want. That means that this expression is valid for all z in the complex plane. We can use this formula to develop the Maclaurin series for other functions as well. Consider, for example, a case when f of z is equal to z squared multiplied with the exponential function of 3z. Again, we are going to consider z0 equal to 0, which is the case when we have a Maclaurin series. Then we already know what this is, because we know the expression for the Taylor series in the case when we have the exponential function of z. So in this case we can just replace this expression by 3z instead. And this we have done Here we are replacing set by 3 set, and of course we have to multiply with set square. And this set square can be multiplied with each term of the infinite series, and what we then obtain is just we can replace this times set square by 3 in the power of n over n faculty multiplied with set in the power of n plus 2. Let's consider another example. The function f of set equal to as we did previously, we define it equal to the exponential function of set, but in this case we let set 0 be equal to 0, so we are not considering the Maclaurin series anymore. So in this case we have that the nth derivative of set 0. What is that? Well, it's easy also in this case, because the nth derivative of set for any value of set is equal to the exponential function of set. So in this case set 0 is equal to 1, so we have that this nth derivative is equal to the exponential function of 1, which is just this. So now we're replacing in the general formula. Let's go back and just recall. This is the general expression for this an, and now we have that this guy is equal to the exponential function of 1, and this is always equal to n faculty. So what we are obtaining then is just this. This exponential function of 1 over n faculty multiplied with set minus this set 0, which is equal to 1 in this case, in the power of n.